So yeah, just remember the dates for everything. We've got some late things can be due tomorrow if you want to get it in before midnight. Remember that our final is going to be on the Tuesday of next week. So you're going to come into class at the same time and you're just going to take the final and leave. We get the room from 3 to 4:50. That's when it will be. You'll come down here to this module and click start on the exam just like for the midterms. So yeah, that's how that's going to happen. And yeah, all that I have today is to get through these slides with you. And then the rest of the time will be all yours to ask questions and work and do fun stuff. But let's pick up where we left off. We were talking about recursion. I would like to do an example of recursion on trees this time. So I'd like to make a function that counts the number of leaves in a tree, and that is a recursive problem if you think about it. So I have an example that I've just pre-programmed it. Apparently I needed more time, so I'll give you the code in a second. But let's think about it. Let's say we've got a tree. Like here's the root of my tree. It's got a 5 node, let's say. It doesn't have to be a BST. The leaves still exist in non-BST, just normal trees. But I'll draw a BST for fun. Let's say we got this tree. All right. There are 1, 2, 3 leaves in this tree. Yeah, 3 leaves. We like to count them. It is recursive. We can see that this could be recursive. Let me show that to you. Let's see here. Boop. When you're looking at the recursive case, like you've got a tree, you've got lefts and rights, you can assume, right, when you go down the left side and the right side, you got smaller trees, smaller subtrees, you can assume that the recursion gives you back the correct number of leaves in each of those subtrees, right? You just get to assume that. They're smaller things, it'll all work out. So you can expect your recursion to give you back, there's 1 leaf in this subtree, right? It'll find it. And there's 2 leaves in this subtree, it'll find it. How many leaves are in your entire tree then, is the question. You see how you can use those smaller answers to build up the bigger one? That will give us a recursive case. So I would like to make a function called count leaves. And the recursive case is going to be count the leaves in the left subtree. And then add that to the sum of all the leaves, the number of leaves, in the right subtree. Just like that. Okay, then we need to think about a base case. So when you get down to the smallest levels, like you got like a tree, like you get to this subtree, right, 3, 1, you're going to be calling stuff, right? 3 is going to make a recursive call down this subtree, down the subtree with 1 in it, and then there's nothing to the right of that 3 node. It's gonna try though, right? That's what the recursive case does. It's got a left and a right at least. So let's figure that out. So like this subtree, when we go down this side, we should be giving back 1, right? There's 1 leaf in this subtree. It's the one and only node. And then when it goes down this subtree, are there any leaves over there? There are not. So that kind of gives you 2 ways of, like, that kind of helps you differentiate potentially what's going on here. If you have a leaf, you see that there's going to be 2 different base cases now, because these both won't work the same otherwise. If you have just a leaf by itself, that is 1. You can notice that immediately. You can say that there is 1 leaf in this subtree. It's just me. That's it. I am the leaf. And then if you go down an empty tree, then there is no leaves. If you let yourself go down that way, there are no leaves anywhere over there. So that's your base case. Base case is plural. Plural. You see an empty tree? There are 0 leaves in an empty tree. If you see a leaf, there is 1 leaf, and that's you. And the reason we need that is because you can't let the recursive case run in like a leaf case. Because like the second you did that, like, okay, go down this side, go down this side. My number of leaves is 0 plus 0. See that? You would have had to stop it sooner. We need another case for just the leaf. So yeah, that's how you notice that, and I hope that makes sense. And so here's some code with that in mind. I've made this exact tree. It's a little disgusting, but we're making it up of tree nodes with datas and lefts and rights, forgetting about parents. And so I've made this exact tree, and we're going to run count leaves on the root of that tree. And here is the count leaves function. So if you got an empty tree, 0 leaves. If you've got a leaf, where the left and right are null, that's how you know it's a leaf, return 1. There's 1 leaf, I am the leaf, base case. Otherwise, recursive case, I need to give back the sum of the leaves in my left subtree and my right subtree. And that should work. That should give back 3 for this tree. Boop. And there we go. Are there any questions about that code or how we came up with the algorithm? Recursion is weird, but with enough examples, it should make sense. All right, and that's, I think, all that I wanted to say about recursion for now. We good with that? All right, let's next talk about, still remember all the old stuff. The big three, remember the copy constructor, copy assignment, destructor. The second you override one of those, you better mess with them all. And the problems arose when we had heap memory involved. We made our own heap memory. We need to clean up ourselves. In the destructor, we need to make sure to not do shallow copies and the other things. Very important. So I'm just going to make a silly class. We used holder as an example before. I'll make a holder that holds an array this time. Why not? All right. So I'll make a holder R class that holds an array of a certain size that we specify in the constructor on the heap. So like this is the normal constructor for this class that I want to make. I'll say holder. This will be the type holder of arrays. Of one array, like H, give it like 42, and its job is to make, it's got a array pointer called R or something, pointing onto the heap. Boop. And that should make an array of 42 things that I can then go and mess with. So, slight upgrade from the old holder example. So, before we code this up, let's figure out what else needs to happen. So a copy constructor is you give me some other holder R, I guess. This time is what we'll call it. You want to build a new one in the image of an old one. If I can spell holder. You give me, like, make H2 out of H. The job is supposed to be H2 is going to be a little stack memory variable. It has its own array pointing to not the same one, right? Because then you got, that's a shallow copy. Don't have it point to exactly the same address as H's are. Have it point to another array, right? Have it point to a brand new array that we make on the heap. Oops. Brand new array that we make on the heap, and have it be of the same size, right? Same size as H's array, so maybe we need to save the size as well. And like copy it all in, deep copy, right? Deep copy it right there. That should be the copy constructor. Yes? Don't make an example, a shallow copy, which would have been something like that. We don't like that. Okay? Copy assignment would be like, all right, let's say I've made, I don't know, I've made another H3 somewhere, and I really would like to be done with whatever H2 is right now. I want to set H2 to H3. So the job of that is supposed to be, right, you want to delete yourself, get rid of all your old stuff because you're going away. You're going away and you're bringing in H3 stuff wherever H3 was, okay? So it's like you get to get rid of this guy, get rid of this on the heap first though, like delete this, goodbye, chop that off, and then do like a deep copy of whatever H3 was. Maybe it was like a slightly shorter array or something, and copy all of its elements in. So like copy assignment is kind of a combination of the destructor and the copy constructor in that sense. You get rid of what you used to have, you're bringing in new stuff. Essentially, destructor plus copy constructor. And don't forget the self-assignment check. And because that'll burn you, right? Self-assignment check. Because if you did H2 equals H2, like if you played this game, you would have deleted your own array and then tried to copy it back in. That would not have gone well for you, okay? So on picture, on the slide, in picture form, do all those ideas make sense before I code it up? All right, let us do it. So I'll make a new file. And I guess I'll call it big 3. All right, so let's make the original, just the first normal constructor. Like, here's what I want. Here's what I want to be able to do. Let's pretend I've got everything first, maybe. We'll make a holder of arrays, H, size 42 array. I want to do a copy constructor, make H2 from H. And that's a call to the copy constructor. I would like to make maybe another one, H3. So this one should be just normal H. Make an H3, also size 42, and then I should be allowed to copy assign things like H3 equals H2, something like that. And then also the self-assignment check should work out, and we should be able to do H2 equals H2, and that should have no effect at all. Okay, so those are both copy assignment. Okay, that's what I would like to have, and yeah, let's make it happen. I'm gonna be lazy and do it all within the class, but a good exercise would be to do it outside. So what does a holder R need? It needs to hold on to its array on the heap, int array on the heap, and then also we're gonna need the size of that array, because when I want to copy stuff, just this is not good enough to know how big it was. It's just that's the pointer to where it began. I don't know how long it was. So arrays don't know their size in C++, so we will remember that size separately. So there's that. And I'll just make some constructors in the body. So int n. So if you want a parameterized constructor, you give me the size of this array you want to make for me on the heap, then I will set my member variable r to be a new int array of that size, and I'll set size to n as well. So that'll work out. And yeah, next comes the copy constructor. You want to make a new holder array out of another holder array that already exists. That was this call down here, right, like that. I could have also said the line holder h2 equals h. That's also a call to the copy constructor, surprisingly. It's because I'm creating h2, like it lets that syntax work out, and it's essentially the same as this. It legitimately is. So const holder r reference other. Just want to use it and look at it. So our job, when we're building ourselves again, we've got an R and a size to set again for ourselves, but we've got other, we want to build it in others image. So we want to deep copy others R into our own, and also the size. So our size is others size now, and then our array is a new int of that size that we just set. And then I want to copy over all of the elements, index 0 and index size -1 from the others array into my own now. So I made sure to have just as many. And so r of I equals other r of I. Just like that. So that's going to be our copy constructor. Does that make sense why that's a deep copy? As we're getting there. So the next step is the copy assignment operator. So given somebody else, bring them into me and get rid of whatever I used to have. And then I also return a reference to myself, just in case I wanted to chain assignments. That's just a normal thing to want to do. So holder R reference is what I return. That's the type. Operator equals, you give me another holder R, and I'll copy it into me after cleaning up. So first of all, watch out for self-assignment. Otherwise, this line will delete you. So the way you check, am I trying to copy myself into myself, you can use addresses. So if the address of other is equal to the same address as me, which is this, right, then I will just be done. I have to return a reference to myself. That's the one thing I need to do. So I'll say return star this, and I am out of here. Otherwise, if we're still good, it's some other person that we want to copy into ourselves, some other address of a holder R, then we want to kind of do a destructor plus a copy assignment. So we'll delete our current array, delete our own array, I'll just say array. So it's delete bracket bracket R, right, because it's an array of things, not just a single thing, not just a single int. And then we can do the deep copy, right? Deep copy other stuff into ourselves. And that's more or less me copying the copy constructor. And I just do that more or less, yeah. I can run all this code all over again. And then my job is still to return a reference to myself when I'm done. So that is. So that is the copy assignment. Seems right to me. Questions about that one? See how that needs to work? It's ingrained in our minds now. Because the last piece of the puzzle is the destructor, right? What happens when a holder R goes away? What else do we need to do? Well, the one thing that we have managed ourselves, the one memory that one place in memory that we are like doing ourselves and managing is this R. So that's what I need to get rid of. The only thing I need to do is delete the entire array R, which is a delete bracket call. I'll get rid of that. All right. And so, yeah, that should be everything. We shouldn't segfault now when I run this code. And we also shouldn't leak any memory. So we can check that. So there's no output, of course. Oh, we didn't segfault. And if we say val grind leak check equals full, try to run it. No leaks are possible. That's what we like to see. So I think that's what I wanted. So that's the big three. Big three in a nutshell. When you mess with heap memory, you have to overload all of these things. The defaults don't work anymore. They would have made a shallow copy and they would have ruined a lot of stuff. Yep. Any questions about any of that? So we're almost done with the old stuff. The last thing I want to talk about is just like complexity in general. Don't forget all those things. So there's a cool website. I think I maybe showed you before. It's called bigocheatsheet.com. Kind of gives you a bunch of data structures and also sorting algorithms, and they give you some average case time complexity, worst case time complexity, worst case space complexity, and most of these things are correct. All right, do look at, remember that we implemented, first of all, singly linked lists in this class, next pointers, not previous pointers, and some of these things, like we studied mostly worst case. Some of these things are a little complicated and not maybe correct. It depends on the list insertion and deletion. It depends on where you're doing the insertion and the deletion, we know. So like for singly linked lists, insertion and deletion, it's saying is constant. That is not true for, well, it's true for insertion, right? It is not true for deletion, right? Because it popped back on a list. If you try to delete the last node, it's going to take linear time to go and find the second to last thing and make that the end, right? So with a grain of salt, it's probably assuming like you want to insert at the start or something. What's the worst case for inserting in an easy place? The best worst case maybe for any kind of insertion. So just take that with a grain of salt. But most of these are still correct. The trees, just like a binary search tree. See how it says O of n here for all the worst case times? That's exactly what I was talking about before. That's like, it's assuming that your tree n is all you get, and like your tree in theory could look like this, where the height of the tree is the number of nodes essentially. And I still think that O of h is a better analysis, and so that's why it says that, but keep that in mind. But yeah, if you have, on average, a binary search tree will be mostly balanced. On average, it's balanced. So that's logarithmic time. That's wonderful. And then same with like hash tables. We know that the worst case time for hash tables, if you have a horrible like insertion, like if you have collisions all day long, and you're packing n nodes into every index, if you only have like 2 indices or something, you will get linear time worst case, but usually that never happens. You're going to get the average case times of constant, which is lovely. Okay, so yeah, just remember those. Just go back to that. That will help jog your memory at least. And I think that's what I wanted to say. But yeah, just remember that list insertion and deletion, it really depends. So like if you had a list, you know that you got the front and you got the end, you got the first and the last. But if you want to go and get rid of the last node, you got to do the following. You got to get rid of that thing. You got to call delete on your last node, which you have a pointer to. And then you got to go searching for this guy. which is linear time to get there, right? And then also you got to set its next pointer to null now. So yeah, I think that's what I wanted to say. So that's complexity. Just remember the complexities for the data structures that we know and love. Okay. Yeah, we're ready for stuff after any midterm we've ever done. So that's most of it. So we've got the first big thing is heaps, right? Let's talk about heaps. What do I want to do there? Do I want to write any code? Maybe in a second. So yeah, heaps, the data structure is completely different than the heap dynamic memory location, right? We use heaps to implement the priority queue abstract data type. That's important. And all it is it's a tree, and we're going to store it in a vector, and that's going to force it to be a complete tree, which, remember what complete means, is like every level is filled in perfectly except for maybe the last level, and that last level is filled in from left to right. That's why we made up that word for this reason, okay? This is what it's good for. So an example of a min heap, because you could also have a max heap, it's when you're going to prioritize smaller things to the top of you, and that's going to push up the smallest thing at the root of this tree. So maybe 4 can go here, 42 can go here. Does not have to look like at all a binary search tree. Like 5 could go over here just fine. That's not a problem. Then like 47. Yeah, the bigger thing to the left does not matter, as long as it's like the smaller things are above you. So like 88 could go there, 100 could go here, 256 could go here, 112 can go there. All right. But the way we're storing this is secretly in a vector, and so this is going to go at index 0, index 1, index 2 is going to go in level order, and we can calculate those indices. We can move around the tree by doing index calculations. So really, you're storing this heap in your little heap array, right? Heap array. And it looks like this at the start, at least. I can't draw it all. So like here's the start of that array. It's got the node 4 at the start. You got the 4 node. That's where that one's going to go. Then the 42 node. Then the 5 node. Then the 47 node. Da da da. Yeah. So you can move around the tree with indices. You can always go to the left index of where you're at. Say you're at index I. You can always say like left of I to get to the left subtree, the left child of somebody at index I. That's always going to be equal to, you double your I and you add 1. That will work for anybody. What's the left index of 0? It's 1. 2 times 0 plus 1 is 1. You want to go to index, like you're here, you want to go to the next, you want to go to the left subtree, so the left of 2 is index 5, that's 2 times 2 plus 1. It's perfect. It'll always work out the same. You got formulas for right, you got formulas for parent as well. It's all there, and yeah, it's going to force the highest priority thing for whatever your definition of highest priority is to the top. So normally we think of this in terms of mins and maxes. So yeah, what can you do to a heap? And what are the analyses of all of them? It's a lot of logarithms in terms of the analysis for running time, because this tree is guaranteed to be packed and balanced, right? It's going to be complete. And so the size of it is always going to be proportional to the log base 2 of the number of nodes, which is wonderful. So the lowest leaf, the height of the tree, log base 2 of the number of nodes, which is lovely. So yeah, remember that here are all like your operations. You want to be able to push a new thing onto the heap. That should always be a possibility. That is just the idea of like adding a new node and bubbling it up to where it needs to go, because maybe it's smaller than things that are above it. So that's, maybe it needs to move up the whole height of the tree, logarithmic time because of that. All right. Popping is getting rid of the root. You always want to, the heap is prioritized around the root, right? So the root is the one thing you can get rid of and look at with peak. Peak is like constant. You just go to index 0. But popping from the heap is getting rid of the thing in index 0, which is going to involve like, you got to swap it, right? Swap the last thing with the root, like put the 112 up here. Then you can put the 4 down here, get rid of this last node, and then you got to bubble this down to where it needs to go. So like put the 5 there, and then the 100, and it'll all work like that somehow. Okay, so because of that, you might have to bubble it down the height of the tree. That's logarithmic time to do it, swapping at every level along that path to maybe the lowest level. So And then to see if like your heap is empty or to see how big it is, those are both pretty much calls to dot size on the underlying vector. And that's constant time stuff. Maybe an extra check equals 0 on the dot size. Yeah, so those are both constant. But anything that does any heavy lifting like bubbling up or down, that's logarithmic. And so that's wonderful and pretty much as good as you can do if you have those operations in mind. So the priority queue ADT is best implemented by a heap because these running times would just get much worse if you didn't use a heap. Yeah. Yeah. Any questions about that before I draw some pictures of those operations? All right, let me see if I can get away with copying this entire heap. I think I can. So we're going to do push a picture of that. We're going to do pop a picture of that. And that'll be that. All right, so let's do push. So what push should do when you're pushing to a heap is you're going to push back to your vector. So you're going to add a new node to the last place in the heap array, so like index 8, which is going to go to like the bottommost level, and you're going to go to the like leftmost open index. So like you're going to go to the right though, right? Bottommost rightmost location you could possibly put it and keep it complete. So that's going to go here, all right? So 8, index 8, and then you push what you want to push there. So maybe like we want to push, let's say 3. That's a new smaller thing. So that'll give us the worst case complexity. So then you need to respect the heap property at this new location, right? This node is thrown off the heap. Now we don't have a heap anymore. So this node is smaller than its parent. So it should be its parent. And we have to keep playing that game. All right, so we want to bubble that node up the tree until the heap property is correctly maintained again. And what bubble up means is you keep on looking at your parent, which is like your index -1 over 2, something like that. You keep on looking at your parent, seeing if it's a min heap at least, seeing if they're bigger than you and swapping if they are, and just keep doing that in a loop until you get to potentially the root. So yeah, what's going to happen is we're going to see the parent of 40 the 3 node is 47. That is bigger, so we should swap. So 3 can go here now. 47 can go here now. And then we're here, and we want to play the same game in a loop because we are still smaller than our parent, and that's not good for a min heap. So we'll swap again. So 3 gets swapped with 42. Just keep on looping until you're at index 0, right? Because then you can't go up anymore. So now we're from the perspective of being at this node. We look at our parent. Our parent's still bigger than us. That's not okay for a min heap, so we need to bubble up one more time. 3 goes there, 4 goes there, and then your loop should stop because index 0, there is nobody above you. Okay? So yeah, that'll be how that works. And it was logarithmic time because you got a balanced tree guaranteed, and you're moving up potentially all the way up from the lowest leaf. You're guaranteed to go from the lowest leaf always, right? Because you just added a new leaf on the last level, up to potentially the root if you added a new minimum thing, perhaps, in a min heap. Okay, you're going up the height of the tree, which are, there's log base 2 number of levels, and you're doing constant work at each level. That's just a single swap. Okay, so that's why it's logarithmic. Does that make sense to us? Questions about that? All right, and then what else we got? We got pop now. So if you want to pop, it's always the root we're popping. So if you want to pop the root, you think of it in terms of swapping, but you don't really have to swap. It's just like you got to keep the 112. Like you're going to use the last index to get rid of the first index. So you think of it as swapping, but you don't really have to do the full swap. You just really need to put 112 up here. So you swap the root's key with the bottommost rightmost node. So you put the 112 up here. You don't have to put the 4 down here if you don't want to, because you're about to get rid of this node. But conceptually, we'll think about it as swapping. And then we're good to pop back the vector, because like the bad thing we don't want anymore is now here. Goodbye. So we only have indices 0 through 6 now. And then our job is to get that 112. That's another element in the heap. Get this to where it really belongs, because it's probably too big to be the root. So we're going to bubble it down this time. And bubbling down is a little bit more complicated than bubbling up because we have 2 children to look at potentially, right? 2 children to look at, and we want to swap with the smaller one if it's a min heap, because the smaller one should be prioritized. So yeah, bubbling down means repeatedly looking at both of our children and swapping with the smaller one. You also you have to play a game with indices as well, because maybe you don't have any children. You got to check that in terms of like indices in your heap array. And you also need to notice, like, sometimes you maybe only have one child. It's guaranteed then to be the left child because of the way complete trees work. And then you need to make sure to only go to that index and not the other one. So it gets a little complicated. But when you got two children like this one, like, okay, my right child is index 2. I have that one, so I'm guaranteed to also have index 1. So go to left and go to the right as well. All right, so we're here. We want to bubble down. We see our two children. We got two children. Who's the smaller one? Because this is a min heap. It's the 5, so we'll swap with the 5. So 112 goes there, 5 goes there. And that's the new root. And then now we're here. And maybe we're still too big to be here. And so we'll look at our children. Do we see anybody smaller than us? We do. Who's the smallest? That's the 100. So we're going to swap with the 100 and put that. We're going to go down this side. 112 goes there now. 100 goes there now. And then we're here. Like, our loop would stop now because there's no index to the left of us, which would have been, what, 8, 9, 10. It would have been index 11. 11 doesn't exist, so we don't even have a left child, which means we don't have a right child for sure. Therefore, we can stop. We're at the lowest level for ourselves to be at. And so that was us bubbling down. And again, it's log base 2 of n because maybe that thing that you just made the root was so large, like the largest thing in the heap, and you need to go down to a leaf again. And so that was going down the height of the tree, which is proportional to log base 2 of the number of nodes. Nice. So yeah, I think that's what I wanted to say about pop. Is that coming back to us? Questions about pop? So the implementation we know is kind of weird and disgusting, but at least conceptually, it's not too bad. So that's pop. Then we have sorting. All right. So let's talk a little bit about sorting algorithms. We'll watch the pictures one more time. I just kind of want you to understand the running times, the basic ideas of these sorting algorithms. Bless you. I would not want you to memorize the algorithms. That's more of a later class. So I just want you to have the conceptual ideas down. So yeah, just remember the ideas behind all of them. Like, bubble sort was the most naive. It's probably the easiest one to implement, though. It's n squared, average, and worst case, because it's always playing the same game. It does not know when it's finished. It's does it the worst case number of times always. Dun dun dun. Let's see. There's a way to make it linear time if the array is already sorted. But you have to keep track of some extra stuff. I don't know if I want to. I don't even think the analysis this one has that implemented. But if I click bubble sort, it's always it's looking at things right next to each other. It's going to keep swapping elements that are right next to each other if they're out of order. It's going to keep doing that as much as it can. And every time it does a round through the array, it's moving the biggest thing, right? The biggest thing in the rest of the array that it's looking at so far. It's going always to the right. That's going to be prioritized because the thing that's out of order, right? If they're out of order, it's going to get swapped to the right, to the right, to the right. The biggest thing is always going to end up at the right side. And so you're always going to put one thing after you've gone through the array once. You're always going to put one thing in the right spot, but everything else, like this 4, for example, that's right here, it's so small. It's only going to move to the left once every round. And so if you had the smallest thing on the right side of your array originally, it would take n rounds of going through the entire array and doing swaps to move that to the left where it belongs. And so that's why you're doing linear work essentially on average every time you go through this array that's getting smaller and smaller. And in the worst case, you have to do that n times, and so that's why it's n squared. All right, so it's getting its way there. Yay, we did it. And yeah, naively, this doesn't notice that you can keep track of, did I do any swaps this round? If you did not, you can stop early. So that's one way to make it a little bit faster, but that's not what this one's doing. It's just it's naive. But that's bubble sort. Yeah. In this case, if the array is sorted, keep track of whether you did any swaps this round. Something like that. So there's that. Then we've got selection sort. Selection sort was also n squared. What it's going to do is it's going to select out the minimum value. It's going to go through the entire array and it's going to find the minimum thing and put it at the index where it belongs. So the first time it's index 0, it's going to put the minimum thing in index 0, then it's done filling in index 0. Then for the rest of the array, so there it is, put it right at index 0. It's going to go through the rest of the array now. Now it's working on index 1. It's going to put the smallest thing in the rest of the array there. And do the same for index 2, 3, 4, 5, all the way down until the end of time. It's going to select out the minimum in the rest of the array, put it at the next index it's trying to fill in. And so for similar reasons, it's got to go through that rest of that smaller array, which is on average of size n. It's going to go through that n times once to fill in every index. So that's why it's n squared. It's getting there. And the constant out in front of that n squared is much better than for bubble sort. And so we prefer this one. Bubble sort is the one we never do if we can avoid it. So yeah, but it's the first one that we like to learn though. Easy to prove that it's right. Questions about bubble sort, selection sort? You see, like, remember the basic ideas? That's all I care about, you know. Insertion sort was the most complicated of the n squareds. It was n squared average and worst case, but it does have a best case of linear if the array is already sorted or almost sorted, because it just needs to move things a constant number of times each round. But what it does is it keeps track of a locally sorted subarray. After every round, it's going to it's got an outer loop. It's always like it's expanding its frontier. It's bringing in a new element that it has not seen before, and it's moving it down to where it belongs in that locally sorted subarray that it's keeping track of. So after it's done an iteration of its outer loop, we go back to the code, like the first original elements of, like the first I original elements in that array are sorted. And so if I randomize this insertion sort, you're going to see like an increasing subarray as it's keeping track of things. It's always bringing in a new element down to where it belongs, down to where it belongs. Bring in this one down to where it belongs, down to where it belongs, down to where it belongs. So like this is increasing, this is sorted, and it has not looked at anything over there yet. That's how that works. And so if it's almost sorted, you can see why it's linear, because it only needs to move things down like a constant number of times each round in that case. But that one had to go at the start. So it's expanding its frontier, bringing down the new thing to where it belongs, doing a lot of swaps. And so you can kind of see for similar reasons why it's n squared. You might have to move everything down in the worst case to the start if it's backwards or something. And you got to do this for every index. And so there it is. But if I click it again, it'll notice, like it'll bring in the expand its frontier. Is the thing to the left of me any smaller? Oh no, I'm good. So I don't need to move it down. And then it's done. So linear time if it's sorted or almost sorted. That's insertion sort. Yeah, just shout out if you have questions about this stuff. The most complicated ones were the divide and conquer recursive ones. So that's merge sort and quick sort. They are both n log n. Merge sort is n log n always. Worst case, best case, average case, because it's always going to do splitting in half. It's always going to do it perfectly, cleanly in half. So here's my diagram of merge sort, the way I like to say it. We got no, let's draw this first. So we've got an array we'd like to sort, just in the world's smallest diagram. We are going to split it in half, always in half. And then we're going to recursively call merge sort on the left half of that array and the right half of that array. So we are guaranteed to get back when we call merge sort twice a smaller array, right? Smaller array. The magic of recursion lets us know that these two smaller arrays are now sorted. And then we get to, we need to bring them back together. We need to merge them together. So we sort the smaller things, then we merge them back together by, playing the game of, we're going to compare, because at the first one, if we're trying to fill in, for example, the first index, we're merging back. We want to fill in the first index of the bigger thing. We're just, the only possible thing that could go there is either this smallest thing or this smallest thing. One of those has to win. Put that one there. So it's a linear time thing to do the merge, and the recursion tree can get, it's a question of how many times can you chop your array in half and still have something there. Logarithmic in terms of the number of elements for that, and then it's going to be linear work at each level of the recursion tree, and so it's always n log n for that hand wavy reason. All right, And so we can watch it work. And it does need some extra space. Merge sort needs some extra space. It's going to use a little helper array down here to do its merging, and then it's going to copy it back into the original array. But you can watch it, like highlight what it's working on, and eventually get down to the base cases where it's like a size 1 array. That one's already sorted. Let's return, and now we can merge that back into something bigger. So it's just recursively merge sorting, and then it's merging. You're watching it merge when it's doing stuff down there. Merging, merging. So now the left side of this array is sorted. We're working on the right side recursively. Almost there. Now we're merging the two left and right halves. And so that is n log n. And it's always n log n. It's always going to chop in half. It does not know that it's done immediately. So that's merge sort. And then quick sort was the most complicated one to explain, I would say. It is recursive. It doesn't do it in a normal way, right? It has it's got a partition function, and that takes care of a lot of things. And you kind of need to bank on the partitioning being nice and evenly partitioned. So you could have a worst case that is not n log n, but that's hard to get. It's going to be n log n on average and in the best case. So what quicksort does is it partitions based on a pivot element. It picks it should be picking a random element, and so that's why it's going to never do a bad partitioning on average. But if you pick a bad pivot element each round, you're going to rearrange your elements around that pivot element. You're going to put things smaller than it to the left, things bigger than it to the right. And so if you pick randomly for your pivot element, like kind of the median value of your array, you're good to have like a left side and a right side, everything that's bigger and everything that's smaller on each side in the right spots. And then that was cut in half, and then you can recursively quicksort on those halves. So let's just watch it work. So you're going to watch it highlight a pivot. It's this element, and it's going to put everything smaller than that pivot to the left, everything bigger than that pivot to the right. That's doing the partitioning right now. And then it's just going to recursively quicksort the left and right halves now that we know everything bigger is over here, everything smaller is over here. And so it's slowly but surely putting things in the right order that way. But if you have a bad pivot element, you'll get a bad partition, and then you're going to get n squared for this kind of reason. Here's your array. Say you horribly, unfortunately, always pick as your pivot element, the thing that should really go, let's see. If you had a good pivot element, it would be this middle thing. It would partition your array into a equally sized left half and right half that are less than that thing and bigger than that pivot element. But if you were to pick something over here, for example, then you quicksort the halves. If you were to pick something over here, you'd all right, you put everything smaller, the one thing over there, everything over there smaller, and then you go quicksort that, and you quicksort the right half. That's just really big still. It's pretty much n-1 size now, n-2 size now. And if you keep playing that game and getting a bad pivot element that ends up right here, and then you're going to keep on having a lopsided partition, and you're having to quicksort recursively arrays that are not getting cut in half. And so the recursion would, the depth of that recursion would be size n/2, and that would be bad. That would, because you're doing linear work at each partition, all the elements in each array. Linear work at each level of the recursion tree. If the recursion tree isn't getting cut in half like merge sort is guaranteed to do, then you have problems. All right, so that is my high-level idea of what could go wrong. But usually, if you pick a good random pivot element, you move everything to the left that's smaller than it, and everything to the right that's bigger than it, you've more or less chopped your array in half, and you are good to go. All right? Any questions about our sorting algorithms and their ideas? I just want you to know the high-level stuff. All right. Let's talk about question, yeah.
So for smaller data sets, merge sort faster, and for the larger ones, quick sort faster?
Not necessarily. I would say that they'd be more or less similar. Well, asymptotically, they are the same. But in practice, quicksort is usually always faster than merge sort.
Yeah, but during the demonstration on their website, quick merge sort was consistently faster for some reason.
Oh, that could just be due to how they're doing the animation. Honestly, I'm not sure. Quicksort, the way I learned it at least is quicksort has a better constant than merge sort, and so it's just like it's generally preferred if you can get away with using it. Did you time it? But yeah, I think that's probably just due to the animation. But let's see, what could we do? Could you count? No, you couldn't even count swaps because it wouldn't work that way. Yeah, they're two fundamentally different algorithms, sadly. But for smaller arrays, actually though, the recursion is a kind of a bottleneck. And for arrays that are pretty small, people prefer to do insertion sort actually. Because like the constants out in front of these n log n's, they work out well as you have large things, but like the n squared, which is what looks like this or something, it actually kind of wins based on the logarithm. Like that's those two for a certain size of the problem. Like it's less work to do, which is interesting. Like less calls to functions and things, but eventually these ones are always going to win out over insertion sort. But for small things, people like insertion sort. Yeah, that's a great question. Does that kind of answer? Yeah. Any other questions? All right. Oh, you know what? Actually, I think I have an answer. Like a real answer for why it looked faster. Boop. No, yeah. I think because it's like, I was gonna say, is it gonna? Yeah, I think it's just the animation. Never mind. I was gonna say, did it in the blink of an eye copy that that extra array back to the start? I think that's what it's doing. It's also not showing you the amount of time it takes to like allocate memory for another copy of that array. So that's also not part of the animation. But I thought it did something in the blink of an eye, and it didn't, unfortunately. All right, so let's go to just like terminal command stuff, so that we can get practice with that. I might ask you something about that. So let's do just a few ones. Let's do let's see. Let's do these ones that I've said here. Let's make how do I want to do this? Yeah, let's do first of all, just like let's understand what it means to like have directories and things. So remember just paths in general. When you get logged into the class server, you are plopped into your home folder. Over here, let me just open up a new thing. You're plopped into your home folder. Yours looks like this. And then that is a place that is not, it's like a folder that's just yours, but there's other people in the system. It's like there's the root directory, there's a folder called home, and everybody's home folder is within that folder. So that's my username. So there's a concept of, right, the root directory where a bunch of things are. You can cd there, right, and go to places. My print your working directory. It's just the root directory. There's a bunch of weird stuff there. That's where like your terminal commands live. Like dev is like you can access your devices as a folder and files inside that folder. It's weird. There was home, right? And like there were other people's usernames in there. These are just folders on the file system. This is your root directory, and you know why it's called root now. Like that was my folder. Maybe I gave my cat a username. And then you can make folders within your home folder. Of course, you've done that for every lab. There's other folders. etc. People pronounce this as Etsy. You hold like configuration files there. You've got like bin for binaries, and that's like your default commands live there and other places as well. Like those are places that you can go to. You can cd there, like cd what is in etc. or Etsy. All these things. There's all these configuration files for these things. cd ... gets you back out to the place you were. What's there? What's in? What's bin have in it? ls. Just a bunch of commands that you maybe have used. And this is just, it's not the only folder where there's commands. Like that's where GDB lives. Nice. For example. And so you can move around with cd, of course, cd ... If you ever get lost, cd tilde takes you to your home folder. That's going to be a shorthand for your home folder. You can put stuff there, whatever you like. All right. And so, yeah, let's talk about just like copying and removing files and making folders and moving things around. I think that would be useful. So let me go back to where we are for today's lecture folder. I'll work in there so you can have all this stuff. Let's do, I don't know, I want to be able to copy files. I want to be able to put stuff places. Let's make a file. So we can make it up here. Then test.txt. And then I'll say like hello world. So there's a file. It exists in this folder now. And you can copy it. You can be like, copy that file to somewhere else, like copy test.txt to another name, test copy.txt. And it didn't have to be in that folder either. Let me get rid of it and show you. Like test copy is there now. I can print it out, and it's going to have the same stuff. Cat prints it out to the screen. If you want to get rid of a file, you say remove rm test copy.txt. There's that. I would like to do that, and now it's gone. I just have test again. To make a folder, let's make dir, mkdir. Says directory is the same for name for folder. Make dir, call it like new folder. And so now I got a new folder. It's right there. I can move stuff into that. So I can mv is the command for moving. You can rename stuff. So move test.txt into a new name, like test1.txt. That's moving counts for that. It's like moving it to a new name or to a new place as well. So let's move it back to its original file name. You can also say move test.txt into that new folder. So just say the name of the folder. It will put it in there with the same name. Boop. If I ls the new folder, well, if I ls the current directory, there's nothing, no test.txt anymore. If you look at the new folder, it's got it in there. I can move the new folder's test.txt. You can do that kind of like slash to get there. Move it back to here. Current directory is a dot. So there's test again. You could also have moved test.txt into the new folder and also given a new name, test1.txt. Something like that. So now not only is it gone, but in new folder, it's been called test1. So you see like all the different things you can do moving wise. So that's what that does. I think that's most of what I wanted to say. You can copy things in the same vein. Be like, let's do it one last time. So let's move test1, like move new folders test1.txt into test1, or just test.txt in my current directory. So now it's back out of there. It's here now. So in new folder, there's nothing. And I can copy test.txt into new folder and also give it another name as well. I can call it test copy.txt with the same kind of syntax as I was using for the other stuff. So that's quite nice. And so now I keep the original one. New folder has the new one. I can move test in there too if I want to. Move it in the new folder, keep the same name. Now they're both gone. In new folder though, they're there. And I can cd into that. That can be my new current directory. I can work on those files if I want to. All right, so that's just like a combination of a bunch of like things, like make a directory, remove files with rm, copy, move, stuff like that. You can get a bunch of stuff at once with the star, remember, like cd new folder. There's a bunch of txt files, like let me print them all to the screen. Star.txt gets all the text files and does stuff to them. Yeah, that's kind of what I wanted to say. Any questions about those like commands, the idea of like where you are moving around? Hopefully we're pretty comfortable with those by now. We should definitely do make files, because make is a terminal command as well that's like looking at a file called makefile with a capital M, and it can automate compilation for us. It is wonderful. So let me have a and then remember that like there's an idea of separate compilation where we go through those intermediate .o files, the compiled form of just those one files, so that we don't have to recompile things when they change. So let me give you an example with one header file and two CPP files. You never give the header file to G++, but you give the CPP file. So let's say I've got, like I'll make a.cpp. Let me write bigger. I'll make an a.cpp. I'll make a b.cpp, and I will put code in them that needs to work together. And so I'd like to do separate compilation on each of these. I'd like to go from a.cpp to a.o, the compiled form of just a.cpp. I'd like to do the same for b.cpp to make b.o. I like that, please. And then I want to link them together. All right, at the very end, I want to link those guys together, those compiled files, into a final executable file that I will call, that's the linking process. I'll call that main or something, my main program. And so I can automate this process of like knowing which one to recompile, because if I only change b.cpp, I don't have to recompile a.o, right? That would waste time. So that's why we don't give things to just the CPP files only to G++. That would have wasted time. So let's make, I don't know, let's make the two files at least. Let's figure this out. So here's my directory. Let's make a.cpp. That calls a function in a library that's defined in, oh shoot, let's do that way. Let's make a new file called b.h. And let's have this be a library that holds number of header file guards. Let's have it have a function called foo. Just a silly function name. And so that's my library. It holds this function and its implementation. I would like to use that in my main function. So I'll include that library, include b.h, to have access to the foo function, and then I'll like use the foo function. Foo on, I don't know, 42. So there we go. And then we got to give an implementation to this foo function in b.cpp, right? So let's make that file. B.cpp. Customarily, you include your header file. That's very important when you do object-oriented stuff, but for this one, you didn't actually need it. But let's give an implementation to foo. And we'll say return like x+1, something silly. Okay. So all these files, they're all working together now. I've got the a.cpp, I've got b.h, and I've got b.cpp that implements the library there. I can show them all to you on one screen, which is nice for once. I like to use them all and make a final program, right? They're all working together. They all are necessary to make the final program. And the first way we learned how to do this was we just give them all G++, right? G++, a.cpp, b.cpp, call it main. And that's inefficient because it's recompiling everything. If I only changed a line like a.cpp, I did not need to recompile b.cpp, but this is just naively doing that. So it does work. Boop, I get my 43 printed out. But it could be better, and we could automate it. So let's make a makefile to do that automation. But first of all, we understand how this code is all working together, right? What we need to do. Let's make a makefile. So let me get rid of that compile thing called main. And then I'll make a new file called makefile. It's just a file, capital M, called makefile, and it lets you like put rules for separate compilation in there. So yeah, comments in makefile language start with a number sign. So every makefile rule has it's called a target name. That's the very first thing. That's the thing you're making is usually the name of the file that's getting created. Then after a colon, you put the requirements. What needs to exist in order to make this target? Requirements come after the colon. And then you give a tab, like your editor should be doing that automatically. Then you tab over and give the body of the rule, which are all the terminal commands you need to run to make the target using the requirements. So, for example, to make a.o, if I want to do intermediate files, I want to make a.o, I need to make it out of a.cpp. That needs to exist first. Then I hit enter and I tab over what's the one terminal command I need to do. It could be multiple if you needed to do something complicated, but it's just one command to do this. It's G++, give it a.cpp, and do the -c to do the compile only, make the .o file. Yeah. And so the second I have that rule, I can say make a.o. It will go looking in the make file, and we'll run that rule. There it is. Ran it. And it made 8.0 in this folder. So that's wonderful. I'll remove that though. Back to a blank slate. We can do the same for b.o. What does it require b.cpp to exist? And how do you make it using b.cpp? Just like that. All right? And then usually you put the most important rule at the top so that you can just say make. Because if you say make by itself, it runs the very first rule in the make file. And so we'll make one called main, because that is the file I'd like to make right now. I'd like to make it out of what needs to exist first. I want the compiled forms of A and B, so 8.0 and B.0. Those need to exist. And then how do I use those to make my main executable file? I say G++ on all of those -o main. That will generate that file for me. Does that make sense? And the beauty of makefile is if I say make main right now, or just make, because it's the first rule, it will go looking for 8.0 and B.0. And if it does not find them, and it won't because I don't have those right now, it will go looking for rules to make those. It's wonderful. It was kind of recursive in that sense. It will go and find the things and make them work. All right, if it knows how, and it knows how. So you watch it making 8.0 and B.0, and then it makes the thing I really wanted. And so that saves us so much time, and it makes it nice and efficient. You just give one recipe for how to do it all just once, and then the makefile takes over from then on. Say /main, you're good to go. Are there any questions about this makefile? See it? And then you're just good forever now. If you change a file like a.cpp, if I change a.cpp, now I've said 43 rather than 42, then I need to recompile 8.0, and the make file is keeping track of like file modification times, and it notices that. If I say make main again, or if I just say make, because like that's the first rule, you'll watch it recompile a.0 only, because it knows that b.0 has not changed because b.cpp is not changed. And then it links that. That's a quick process, but the compilation is kind of slow for large files, especially if you have a lot of them. And so this is like the best of all the worlds. It's noticing when to recompile things. If I say /main again, now I get my 44. It's wonderful. Okay. Questions about that? Do we see it? Like that's the point of a makefile. One of the nice reasons to use it. And then sometimes people make rules that don't actually make things. They're called phony rules. Like a common one that I like to give you in my labs that maybe I've told you to use before if something went wrong is there's a rule called clean that people like to use. It takes no requirements. It just runs a command. It's like another name to do some cool stuff. So clean is a rule that usually you use it to remove all of your compiled files and get back to a blank slate. Usually removes all the compiled files. So for this part of the project, it's just like 8.0, B.0, and main. Those are our compiled files. So we'll say rm and then -f so that it doesn't complain. 8.0 if they don't exist, B.0 and main. Okay. So I say make, and I got all these things in this directory now. If I say make clean, I'm back to a blank slate where I didn't have those compiled files. And if I said make again, it would just like remake them all from scratch. And so that's a clean rule. It didn't take anything, just like it was just a little alias for a certain terminal command to do something cool. That's all. Useful. It's kind of like a little shell script inside of this file. And I think that's what I wanted to say. Yeah, any questions about any of that? We don't have much to talk about left. All right, let's do inheritance. Can't forget that. Let's see. Yeah, I'll do a pre-made example for sure. Let's say, well, first of all, let's explain inheritance again. So what inheritance is all about is you've noticed that like when you're using classes, you've duplicated your efforts. You would like to take away all the duplication into a base class. That's the goal of inheritance. You want to reuse code across parent and child classes, and sometimes you want to treat a bunch of potentially different ideas like their base class. That's wonderful. That's where virtual methods come into play as well. Here's a silly example for like phones. Like we'll make an iPhone class and an Android phone class that will inherit from the base phone class. And like every phone has like a price and a battery life, and we can have getters for those. and we'll make just a silly abstract method called like, is this an Apple product? And we'll just like, we won't implement it until we have a subclass. All right, so like the iPhone class will inherit from phone, and maybe it has some new ideas like what processor are we on right now? It's like the A47 or whatever. Then you have a getter for that. Maybe we'll override the is it an Apple product method, and then same for like an Android phone. Maybe it'll have like a runs Linux method because it's fun. You have access to that, and then we'll override is it an Apple product and say false there, for example. So that's kind of the goal. We've noticed that we've got some things in common that we like to stick in a base class. That will be our phone class. And then that's our price, our battery life. Those are the fields. You can also have methods, and we'll have one as well. And then like the iPhone class, we'll overload that, or we'll inherit from it. It'll take all those things. Oh, goodness. There we go. iPhone class. We'll have some extra stuff like what kind of fancy processor does this one have? Because they like to tout their cool names. And then we'll have an Android phone class. And it'll have some extra stuff as well. So that's kind of what we'll do. We'll put all the common stuff at the start, and then also maybe make some virtual methods so that we can treat things like phones and like know something special about them. So yeah, let me copy in that file so we can look at it. It's called inheritance.cpp. And here we go. So here are all the things. Here are all the things we have here. I think that's all the files we're going to make today. Nice. So, okay, here's the phone class. It's got some stuff, bless you. It's got some member variables that are protected, right? They're protected so that we can use them in the subclasses and have access to them still. That's what protected means. We can say .price in an iPhone, like still get it. And then the public methods will be the constructor. There we go. Getters for the price and battery life. We could have been fancier and made this outside, but I was lazy again. And then we'll make a virtual method. We're going to make a pure virtual method. One called is this an Apple product? Returns true or false. Const as well, of course. And we'll say equals 0 to mark it as pure virtual. This is virtual by itself. If we gave an implementation, we could have like had something that they all like would have by default if they didn't implement things, and this wouldn't have been an abstract class. But the second you have one pure virtual method at least, that makes the class with that in it called an abstract class. That means you cannot make an object called phone. It can't be like phone p semicolon because there's no implementation for this method. And so the compiler won't let that happen. You are now forced to use this as a base class. Override is an Apple product somewhere else and give actual meaning to this method so that you can use it again. Okay? We just know it exists now by virtue of inheriting from phone. That's another way of marking that. Okay, anything that inherits from the phone class that we can treat like a phone object must have implemented this method somewhere. That's a nice guarantee. Okay? So then we got like iPhone, inherits from phone. Maybe it has like a processor model. That's this new member variable. And then like the constructor of that would take everything that a phone took, price and battery life, let the phone constructor take care of those things, right? It'll set them, and then set the new thing for yourself, however you need to. And then maybe make a getter for that thing, and then we're going to override, right? Override this virtual method, like is an Apple product, and we'll say return true, because it is. An iPhone is, okay? Something like that. Does that make sense? So that is what I want to do. And yeah, for an Android phone, similar idea. It's like, all right, we won't have any new fields. We'll have a new method maybe for fun. Like here's its constructor. It will take a price and a battery life, and it will use the phone part of itself to construct those pieces because it knows how. Just reuse that. We'll override as an Apple product to say false, and then we'll have a runs Linux method, a new thing just for Android phone objects. We'll be like, yeah, true, which is wonderful. All right. So yeah, just by virtue of saying equals 0 here on a virtual method, that's a pure virtual method. It marks phone as an abstract class. I cannot say this line now. It does not work. Phone P is an abstract class. You cannot make an object just of a phone type, which is interesting. Kind of cool. Let's see here. What do I want to say? Yeah, so here are my silly examples of iPhones. Like this is the iPhone 42 whenever it comes out several decades from now. It'll be $10,000. It will have a very long battery life, hopefully. They'll stop making them smaller and give them battery lives instead. And like it'll have the A44 processor. I don't even know what they're on right now. Maybe they are almost there. What's the processor called in the latest iPhone? I need to know now. They're on A19. They're getting there. All right. And then an Android phone is much nicer. It still has maybe less of a battery life, only 48 hours of battery life, but it's much cheaper and more accessible. And it runs Linux, so we love that. So, okay. Then we could call things, of course, on these objects. We'd be like, all right, every phone has a processor model and a price. We can get the phone pieces and call the phone pieces out of either the iPhone object or the Android object. You can always get the battery life. You can always get, the price, excuse me, and the battery life. You can also get the more complicated things like the processor model. That was something specific to the iPhone class. We added that. And then they also both have the is an Apple product implemented for them. Okay. And then you have your new stuff as well. So those all exist. Let's run that. Boop. So that was these things, just like that printed out. I think, yeah. The last one was like that. Wait a second. So there should be 6 things printed. Give me a second here. Oh yeah, no. Let me just comment this out so that I'm not confusing myself. Yeah, so that was everything we just said. We can get all those things, and some of those were calls to the base class, the phone parts methods, and some of those were new to the things that we've implemented for ourselves as part of the more specific things about those specific kinds of phones, the iPhones and the Android phones. And then the whole point of having base classes as well is that you can treat your subclasses from the perspective of the base class if you use references or pointers. You cannot like chop things off and actually use phone objects still because that was an abstract class. So you got to treat it like put them onto a vector of phone stars or phone references. So you can do that, like put them there and you can treat them like phone objects, even though you couldn't actually make a phone object, which is fun to think about. Very philosophical. And then you can go into that vector and you get it out and it looks like a phone star still. So all that you're allowed to do, all the compiler lets you do is call phone stuff. And so anything that you want to like share, you really do want to put there, even things that you don't really know how to implement yet, like these virtual methods. That's the whole point of virtual methods. We can treat things like their base class and let the subclasses implementations shine still. Let it come through by having our virtual method table and all that fun stuff. Okay, so that's going to work out. It's going to call the version of this method that was implemented for that particular object that I'm looking at. I'm treating it like a phone. I know it has that. If I've made an object concretely, somebody's implemented that. Call that, please. Call the version that I know how to call. All right, it's in the V table. And so V at 0, that's an iPhone, and that is an Apple product, so it says 1. And you better believe V at 0 will give back false. Like we're getting that code called properly on the fly. It's figuring out which body of which method to call. It's like, oh, it's the iPhone classes one. Go use that because it was secretly an iPhone object. It knew. All right, so you can treat it like the base class and use anything that's defined in the base class, including things that have not yet been implemented in the base class. That's inheritance. That's lovely. Okay, I think that's what I wanted to say. Are there any questions about this code? Kind of see what's going on? Are you override things? Say what's where? Because that leads us to our last little topic we talked about. Last main topic in the class was Huffman coding. The idea we needed inheritance for that, right? So we are going to build it and create what are called Huffman trees, which are really binary tries. Pronounce this data structure as trie, as storing strings along the edges of itself. That's what it's doing in like final things at the leaves, in this case at least. And what a Huffman tree does is it lets us find a nice compact way to represent in binary letters or symbols that correspond to like a file. And so we can compress that file by making the most efficient way, like more frequent things will have less bit string, fewer bits to represent that character. Like vowels, for example, will probably have fewer bits than like the letter Z if we were trying to compress a file that had English text in it. So that was all what it was all about. And so to create like the Huffman tree and to make the code and like get out the codes and things, the very first step was you got a file that you're going through and you're trying to compress, right? You're going to go and find the frequency of every character in that file, like all the letters, all the spaces, anything that's involved. And then you're going to make leaf nodes, Huffman tree leaf nodes for every character, and you're going to push those to priority queue. To priority queue based preferring frequency, ordered by smallest frequency. So it's going to combine things that are infrequent together. That's what it's going to do, so that it saves the frequent things for higher up in the tree, because it's going bottom up. It's going bottom up, starting with leaves. And so the goal is you got a little loop going on. You're going to pop 2 nodes from your priority queue, the things with the 2 smallest frequencies, breaking ties arbitrarily, and you'll combine them into a bigger Huffman tree node, and you're going to have a combined frequency for that node. So that was like, we put the frequency in the base class then, because they all have a frequency somehow, even if they don't have a character involved. And the frequency of that new super node that combines the 2 leaves or subtrees is going to be the frequency of the 2 nodes summed together. And the second, then you push it back. You push back the combined thing. And then you are finished when the priority queue has had everything combined into one place, one final internal node, which is one big tree now at that point. There's one thing left. That is your Huffman tree. All right? And the frequency is equal to the size of the file, as you can imagine. So let's, are you ready for an example of that? Does that all make enough sense? So let's draw an example, and that'll do it. So let's say we'd like to compress the file Hi Mom. We'll forget about spaces just for ease of me doing this stuff. Hi Mom. Frequency. On our frequency table is the first thing. We got to count all the characters. So we got an H character, appears once. We got an I character that appears once. We got an M character, appears twice. And we've got an O character that appears once. So the very first step is we're going to make leaf nodes of each character and their frequencies, and we're going to push them into a priority queue ordered by min frequency. PQ, there's my priority queue. And so I'm going to add the H node, and I'm going to say that its priority is 1, or its frequency is 1, excuse me. That is its priority 2, I guess. I1, M2, and then O1. Okay? That's my first priority queue version. And I'm going to show you every version of it. It's the same thing, really. What happens next is we're going to pop 2 things out of that priority queue, 2 things with the smallest frequency. And so we got a bunch of 1s, and so it's like 2 of those we're going to pick, just arbitrarily breaking ties. Let's take H and I together. Okay? So I'll combine the H and the I nodes into a super node of frequency 2, internal node, and push it back into the priority queue. Push it back into the priority queue. And I'll keep everybody else as well. I got those guys. Make them a little bit smaller. Their frequency, their frequency of this internal node now is going to be combined frequency. Oops. Combined frequency 2. And now my priority queue is going to look like that. It's going to have that in it as well as the other stuff. Amen. So that's my priority queue now. Okay? And then again, we're going to keep playing this game. Pop 2 things with the lowest frequencies, and then push back a combined version of that node. Keep everything else there, of course. And so we need to pop definitely the O now, and then one of these size 2 nodes, just to make it easy on ourselves. I'll pop the M and keep that as well. And so let's combine the M and the O into like a super node. Let's see, how do I want to do this? So like take those guys, Bring them over here. Boop. Make it a little bit smaller. The combined frequency of this new internal node is going to be 3 because 2 plus 1 is 3. Then we still got the old one. Oops. I should have copied and I did not. Paste. I'll show you all the intermediate steps. It's not quite how I wanted to do things. Yeah, okay. Give me a second. This is going to bother me. So apparently if I select it like this, then I can resize it normally, which is very odd. 3. So now they're combined, and then the other subtree is still there. Boop. Copy paste. Oops. Come back. There we go. And so that's what my priority queue looks like now. Does that make sense? Just pop in the 2 lowest frequency things. Breaking ties arbitrarily. I just kept the subtree smaller. And then still play that game where our hand is forced now, right? We're going to pop the 2 things and the only 2 things. They're going to have the smallest frequencies, the only frequencies, and we're going to combine them into the priority queue and push them back. So we're not sure if we're done yet. So we take these guys, combine them all. Oh no, I lost one. Come on. Do I have to start again? Apparently I have to start again. Come on. There we go. So I got these guys. I'm going to combine them together into a big internal node of frequency 5, which is the number of characters in the file, as you might imagine. And push it back into the priority queue. That's my new priority queue. Whee! And now there's just one thing in it, and that is my Huffman tree. Right? That is my Huffman tree. And now I can extract the codes for this file and get everything out as I need to get it out. So I've made a trie data structure. It's a binary trie. So if I go left, it's like there's a 0 in the binary representation. If I go right, there's a 1 in the binary representation. So there's 0, 1, 0, 1. And so that means that honestly everything became 2 bits, but that's still a lot of space savings, right? Because the original characters would have been 8 bits long. And so hi mom will now be, what's the H? How do I get to the H? It's 0, 0, right? So it's 0, 0 for an H. For an I, it's 0, 1, 0, 1. For an M, it's 1, 0. Just like that. Go right, go left, 1, 0. 1, 0. O is 1, 1. And then another M, another 1, 0. So now we've got 2, 4, 6, 8, 10 bits, right? 10 bits. Instead of what it used to be, it was a size 5 file, and every char is 8 bits long, so it would have been 5 times 8 bits normally. Instead of 8 times 5, which is 40 bits. And so we chopped this file into a quarter of its size. Lovely. And that's quite nice. Honestly, you want to use this with larger files because you also have to give the person who wants to decompress this the Huffman tree, and that's going to take up much more than the 30 other bits that you're saving. So you have to be careful about that. But that's kind of the idea. I think that's what I wanted to say. Are there any questions about Huffman coding? It's like the last main thing in this class. Because with that, I think we made it. We made it to the end of class, everybody. And there's only 2 things I want to tell you. The first thing is good luck on the final. Here are many memes that you can look at later, as you're studying, of course. And the very final thing I want to say is, can we all please say thank you very, very much to Caitlin for all her help in this class. Thank you, Caitlin. We love you. And she's still helping you with the study session. So, yeah. Thank you guys for putting up with me for a semester. We're almost done. And the rest of the time is yours to work and to ask questions. We'll be here.